Gaseous equilibrium. So let's take a look at this equilibrium. Water in the gas phase plus carbon monoxide reacts to form hydrogen gas and carbon dioxide gas. And let's say we have a graph representing concentration versus time. Now, if we start with equal molar concentrations of water and carbon monoxide and no products, then which line in the graph represents the concentration of water and carbon monoxide, and which line in this graph represents the concentration of the products, hydrogen and carbon dioxide? So, because there are no products when we start out at 0 time, line 1 represents the products, and of course, line 2 represents the reagents. Now, what is the point in time that the equilibrium first begins on this graph? Time A, B, C, or D. And of course, at point D, we see the two lines become parallel. They don't change their concentration anymore. Reagents stay at the same concentration, products stay at the same concentration. That's because an equilibrium is defined as reversible reactions occurring at the same rate. So the forward reaction is occurring at the same rate as the reverse reaction, and therefore the concentrations of products and reagents don't change anymore. In 1864, two Norwegian chemists came up with the law of chemical equilibrium, sometimes called the law of mass action. The law states that from the balanced chemical equation for a system at equilibrium, one can derive a ratio of product to reactant concentrations that is a constant at a given temperature. So if we have a general equation, small a, small b, capital B, where small a is the coefficient in front of the compound in the equation, and capital A represents the compound formula, the mass action expression, sometimes called the reaction quotient, is the concentration of the substances in the product, and concentration is denoted here by the use of brackets. So when you see brackets, that means concentration, molarity. So the concentration of the substances in the product to the power of the coefficient in front for the products divided by the concentration of the reagents to the power of their coefficients. And that's called the reaction quotient, or QC. If the system is at equilibrium, and equilibrium concentrations are used in the calculation of QC, then QC equals Kc. This ratio here equals the constant called the equilibrium constant. But it doesn't have to be at equilibrium. If QC is calculated with non-equilibrium values, then this ratio divided out is not going to equal the equilibrium constant. Read this question and answer it as you put the playback on pause, then come back and we'll discuss it. Okay, so we have particle models of 3 different reactions at equilibrium. And the question is asking you to arrange these reactions in order of increasing value of the equilibrium constant Kc. Remember, it's products divided by reagent concentrations. In this one, the yellow ball represents the product. There's lots of product. There's very little reagent. So this is going to be a large K value. Conversely, over here, where the green ball is the product, there's very little product, and most are reagents. So the K value for this is going to be very, very small. Reaction 2 has about equal concentrations of both product and reagents. So this is going to be somewhere in the middle. So in order of increasing K, this is the smallest, this is in between, and reaction 1 is the largest. All right, see if you can come up with a mass action equation for this reaction. Put your playback on pause, come back, and we'll discuss it. All right, so remember, it is the product concentrations multiplied together to the power of their respective coefficients divided by the reagent concentration, in this case to the power of its coefficient. So right off the bat, we can knock out answer A because the reagent is in the numerator. So that's gone. B is the same thing, and it's gone. That leaves C, D, and E. Answer D has us adding the concentrations together. That's not a good move, so we'll knock that one out. And answer E has kept the coefficients together with the formula. That's not a good idea either. The coefficient becomes a power of the concentration. So that is going to leave answer C as our answer for this question. So let's answer these questions. What is the meaning of a large K value? And of course, that means there's lots of product, very little reagent. And the reaction proceeds in the forward direction from reagents to products. What's the meaning of a small K value? Just the opposite. The reaction does not proceed well to the products. There's relatively few products and lots of reagent. What's the meaning of K about equal to 1? That's when you have about equal concentrations of products and reagents. And how does Q differ from K? Q is merely the symbol representing the ratio of product concentrations divided by reagent concentrations. K is an equilibrium constant. Q, after you work out the math of products over reagents, may equal K or it may not. If Q equals K, you're at equilibrium. If Q does not equal K, you're not at equilibrium. Okay, for the reaction, nitrogen plus hydrogen yields ammonia. First, write out the mass action expression, and then calculate QC and KC for each experiment. So here's experiment 1. The initial concentrations are listed here. Plug those into the mass action expression and calculate QC. And then do the same with these equilibrium concentrations and calculate KC. And do that for experiment 1, experiment 2, experiment 3. Pause your playback, do it, and come back and we'll discuss it. Okay, so the mass action expression, of course, is this: products over reactants to the power of their coefficients. Now let's take a look at the actual values here. So for the first experiment, QC is 1 times 10 to the 12, initial value, and the equilibrium and KC, the value of Q at equilibrium, is 0.0602. In experiment 2, the initial concentrations are 0 for ammonia, 1 molar for nitrogen, and 1 molar for hydrogen. Q turns out to be 0. And the equilibrium concentrations yield an equilibrium constant of 0.062. And experiment 3, same thing. Wildly different initial concentrations yield a Q value of 4.5. But at equilibrium, with these values, K equals 0.0602. So the question is, does changing the initial concentrations have any effect on the value of K? No. In each experiment, the initial concentrations are very different, but after equilibrium is established, K is the same in each experiment. So suppose the reaction of nitrogen plus hydrogen yields ammonia is at equilibrium. That means your ratio of product divided by reagents to the power of their coefficients, or Q, is equal to Kc at that temperature. Now, let's suppose someone injects more ammonia into the system, just squirts it in. What happens to the value of QC? And what has to happen to the value of the concentrations of reagents and products such that QC equals Kc, or you're at equilibrium? Turn off your playback and think about it, and come back and we'll discuss it. Okay, after more product is added, the value of Q, that's the ratio, becomes larger than K. That's because you've increased the numerator and haven't added any corresponding nitrogen or hydrogen. So now this ratio is larger than K. You're not at equilibrium anymore. And the system must respond to lower the value of Q so that it once again equals K to get back to equilibrium. So the reverse reaction is favored product decomposes to nitrogen and hydrogen faster than the forward reaction occurs. It decreases ammonia, it increases nitrogen concentration and hydrogen concentration, and that keeps going on until Q once again equals K, and you're at equilibrium. Again, let's consider the reaction of nitrogen plus hydrogen yielding ammonia. Write the reaction equation for the reverse reaction for the system. Then from that, write the mass action expression for the reverse reaction. Now, how do the two mass action equations for forward and reverse reactions differ? Pause your playback, try it, and come back. We'll discuss it. So here we have the reverse reaction, where the ammonia, which was a product, becomes a reagent, and the nitrogen and hydrogen, which were reagents, become products. If we write the mass action equations for these two, for the forward reaction, it's product concentrations to the power of its coefficient divided by reagent concentrations to the power of their coefficients. The reverse reaction is exactly the inverse, because the products have become reagents and the reagents have become products. So here's a question. If Kc is the equilibrium constant for the forward reaction, which answer would equal the value of the equilibrium constant for the reverse reaction? A, B, C, D, or E? And of course, it's A. It's the inverse of the equilibrium constant for the forward reaction. So consider this reaction. 2 sulfur dioxide plus oxygen yields 2 sulfur trioxide. Now, if every coefficient in this equation is multiplied by 1/2, what will be the value of its equilibrium constant in terms of K? So think about it and choose an answer, come back, and we'll discuss it. Okay, so remember that coefficients become exponents in the mass action equation. If you're multiplying every term by 1/2, that means you're going to have K to the power 1/2. And K to the power 1/2 is the square root of K. So it would be answer B. Now read this problem, put your playback on pause, and solve it. Then come back and we'll discuss it. All right, on this one, if you notice, the reaction has been reversed, first of all, and that's going to be the inverse of K. And then every coefficient has been multiplied by 1/2, and that's the square root of K. So if you do that, take the inverse of K and then the square root of K, you'll come up with 5.2 times 10 to the minus 5. You will get the same answer if you take the square root of K first and then you invert the answer. Now we'll learn in the kinetics chapter how we can add two intermediary reactions and come up with an overall reaction. Here we're adding these first two reactions, and the nitric oxide will cancel out as we add the two intermediary reactions to give us our overall reaction. So the question is, what is the K value for the overall reaction, which will have this mass action equation? Well, let's take a look at the mass action equation for each of the intermediate steps. The mass action equation for the first reaction is this, and the second reaction is this. And if we multiply them, notice how the nitric oxide cancels out. So when we multiply these together, the net effect would be multiplying the equilibrium constants for each one of these together. And when we do that, we get the mass action equation for the overall reaction. So it'll be K1 times K2 equals 4.3 times 10 to the minus 25 times 6.4 times 10 to the minus 9, which is 2.8 times 10 to the minus 19. Sometimes equilibrium constants are calculated on the basis of equilibrium pressures, especially when gases are involved, rather than molarity concentrations. So there is an equation to convert from the equilibrium constant calculated on the basis of pressure, which is called Kp, and Kc calculated on the basis of molarity. Here's the equation where R equals 0.0821, T is the Kelvin temperature, absolute temperature, and delta N is the sum of the product moles minus the sum of the reagent moles. So here's a question for you to try. For this reaction, PCl3 plus Cl2 yields PCl5, all gaseous. Kc is 1.67 at 500 K. What is Kp? Put your playback on pause, try to solve it, and come back and we'll discuss it. Okay, so what we have, here's the equation. For delta N, it's the sum of the product moles minus the sum of the reagent moles. So there's 1 product mole minus 2 reagent moles. So delta N is minus 1 because we have 1 minus 2. So Kp equals 1.67 times 0.0821 times 500 to the minus 1 power. Of course, minus 1 means the inverse. So if we multiply these two numbers, we get 41.05. That'll be in the denominator because it's minus 1. And it's dividing into 1.67. Divide it out, you get 0.0407. How did you do? Okay, let's consider how the direction of a reaction can change. I want you to read these questions and answer them. Put your playback on pause, come back, and we'll discuss these questions. But first, you think about it. Okay, so here we have the mass action equation, concentrations of C times D, which are the products divided by the reagent concentrations A and B, that equals Q. And now what we're going to do is take a look and see how Q compares to K and which way the reaction is going to shift based on that. If concentration of A and concentration of B are greater than 0, but C and D concentrations are equal to 0, that means your numerator up here is 0, which means the value of this ratio is 0 and Q is 0. Now, since K is always greater than 0, it's never 0 and it's never less than 0 or a negative number. That means Q is smaller than K. Q has to grow in value. This ratio has to increase in value. And if we just think about it, you don't have any product and you have A and B concentrations as reagents, the reaction has to shift to the product side. So if Q is less than K, which we have here, the reaction is going to shift toward the product side to make Q larger in value. Now, conversely, if A and B are equal to 0, that means you have 0 in the denominator, and C and D are greater than 0. Well, if you have 0 in the denominator, the value of this ratio is infinity, right? So Q is going to be, in this case, larger than K. Or taking a look here at the reaction, concentrations of A and B are 0. You don't have any reagents. You just have products. And of course, it's going to shift in reverse to increase the value of A and B, to grow A and B. And that is going to have the effect of lowering the value of Q, because when you increase the denominator of a ratio, the value of the ratio decreases. So Q will get smaller as the reaction shifts toward the reagent side. So in this situation, Q is larger than K, and it's going to shift to the reagent side. So that's what 3 is. If QC is greater than Kc, the reaction is going to shift toward the reagent side. So put the playback on pause, read these two questions, see if you can solve them, then continue and we'll discuss them. Okay, for the first one now, we're going to calculate Q from the initial concentrations and compare it to K, and from that decide in what direction the reaction would shift. So here's the solution to the first one. Q is less than K, and Q must increase to equal K, so the reaction must shift to the product side. For the second one, here's the solution. Q turns out to be greater than K. Q must decrease to equal K, so the reaction must shift to the reagent side. Now, what about reactions that involve pure liquids or solids? How would you write their mass action equations? Well, what are the units of density for a solid, or a liquid for that matter? For a solid, it's grams per cubic centimeter, or for a liquid, grams per milliliter. Is the concentration, osmolarity, for example, moles per liter, of a pure solid or pure liquid a similar concept? We know that the density of a pure solid or liquid changes very little at constant temperature. So would you expect the concentration of a pure solid or liquid to also be relatively constant? Heck yeah, you would. So here's the point. Even if their temperature does change, the concentrations of pure solids and liquids, unlike solutions of gases or liquids, change very little, as does their density. As constants, they are included in the K value and do not appear in the mass-action equation. So, for example, how would you write the mass-action equation for the reaction of calcium carbonate solid forming calcium oxide solid plus carbon dioxide gas? Well, it's just going to be the Kc of the concentration osmolarity of the carbon dioxide, or the Kp if you express carbon dioxide concentration as torr or atmospheres or pressure. The solid calcium oxide, solid calcium carbonate do not appear in the mass-action equation. So let's look at an example of heterogeneous equilibrium where gaseous carbon monoxide is decomposing to gaseous carbon dioxide and solid carbon. And as you can see, we have two piles of carbon of different sizes in these two containers. The amount of carbon is different, but the amounts of carbon monoxide and carbon dioxide remains the same. Therefore, the amount of carbon has no effect on the position of equilibrium. Remember, pure solids have effectively constant concentration. So what do you think the mass-action equation will be? A, B, C, D, or E? Well, if you chose C, you'd be correct. Carbon dioxide as a gas divided by carbon monoxide to the power of its coefficient, so it would be squared. So let's consider a couple of concept questions. Here you have a reaction, calcium chloride solid plus gaseous water yields solid hydrated calcium chloride. What's the mass-action equation for the reaction? Think about it, choose an answer, come back, and we'll discuss it. Okay, you have the solid calcium chloride and the solid hydrated calcium chloride, neither of which will appear in the mass-action equation. You just have the gaseous water on the reagent side. So that's going to be 1 divided by H2O squared. And consider this equilibrium, A plus B yields C plus D. If Kc is a very large number, in what direction is the reaction favored at equilibrium? Products, reagents, or about 50-50? And of course, if Kc is large, that means your mass-action equation has a large numerator, small denominator, and you have lots of product. If Kc is a very small number, just the opposite, and you have lots of reagent. And what would Kc be for a reaction to yield at equilibrium equivalent amounts of reagent and product, assuming the coefficients of the equation are all 1 with equal gaseous moles on each side. And of course that's going to be a Kc of 1.